All right, so good afternoon again, everyone. Today we want to look at alkanes and alcohols. We're still into the series of organic chemistry, and that's what we want to talk about. All right, so let's get right into it. The first thing I want to do is to review with one or two questions before we move forward. All right, so last class we were talking about alkenes, right? And one of the questions, why is the incomplete combustion of an alkene dangerous, particularly in an enclosed space? Now, when we speak about incomplete combustion, it means to say that not all of the hydrocarbon is being converted to carbon dioxide and water vapor. It means to say that there is the formation of carbon monoxide. What this does, this makes things difficult because it can be poisonous, it can be toxic, lethal, and it can prevent the blood from carrying oxygen. In essence, this is affecting hemoglobin, right? But if you were answering this question, you cannot just say that it is harmful, right? You have to say more than it just being harmful. Okay, so part B to the question, the equation for a substitution reaction of butane is given below. Name the organic product that is produced from it. Now, when we speak of the product, this is here what we're talking about, right? They ask you to name the organic product. When we're naming this, the first thing we have to recognize is that there is a chlorine. Now, to identify or name the chlorine, which is a halogen, it has the prefix chloro, right? Then we check and see how many carbons we have. We have 1, 2, 3, and 4 carbons present inside of this compound. So the prefix for that is but. There are no double bonds, so it's an alkane, hence the name chlorobutane. Right now, you could have also named it as butyl chloride, right? Meaning that you looked at this as a C4, H3, 4, 5, 6, 7, H9 group. And this is a butyl chloride group. C4H9 is butyl. The reason for that is because CH3 is methyl. C2H5 is ethyl. C3H7 is propyl, and C4H9 is butyl. So you could have said it was a butyl chloride group, and you would have also been correct. Next part of the question says, this reaction does not need increased temperature or pressure. What is the essential reaction condition? Now we're dealing with an alkene. Alkenes are generally unreactive, so therefore it needs something like ultraviolet light or sunlight in order for the reaction to take place. Next question. The following are two examples of substitution reactions. Only the reaction involving chlorine is a photochemical reaction. So CH4 plus Cl2 to give you a CH3Cl plus 8Cl, and they're telling you that is a photochemical reaction. They tell you, explain the phrase substitution reaction. Now, you cannot just say a substitution reaction substitutes. You can't just say that. What you could say is that the hydrogen atom is replaced by atoms of a different element, or hydrogen has been replaced by chlorine, for example. Right? When we talk about substitution, we use an example to help you explain what you're trying to say. It almost certainly assures that you are getting the mark that you're trying to get. Next question. How do photochemical reactions differ from other reactions? When we speak of photochemical reactions, these reactions require light energy, right? Photochemical reactions require light energy. Next part of the question, bond forming is exothermic, bond breaking is endothermic. Explain the difference between an exothermic reaction and an endothermic reaction. Now, exothermic reactions simply give off more energy than they absorb, while endothermic reactions absorb more energy than they give off. When we talk of an exothermic reaction, they give off more energy than they absorb. Endothermic reaction, they absorb more energy than they give off. So here's an interesting question that is placed before us. It said, use the bond energies to show that the following reaction is exothermic. Bond energy is the amount of energy or kilojoules per mole which must be supplied to break 1 mole of the bond. Right? So in essence, they're telling you that for each bond that is formed, for this carbon-hydrogen bond here, there's energy that is required for it to form. That energy is in the amount of plus 412 kilojoules per mole. Now, the plus sign doesn't mean that it is positive. It means that the reaction is an endothermic reaction. The positive sign tells us that we are dealing with an endothermic reaction. A negative sign tells us that we are dealing with an exothermic reaction. Right? Now, so to form CH, it requires 412 kilojoules of energy. Right? So the bonds that are broken would be the CH. These bonds in the reactant side is the bonds that will be broken. Right? So we have 4 CH bonds, and then we have 1 chlorine bond. Right? We have 4 CH bonds, and then we have 1 chlorine bond. So what we would have to do is we'd have to take the carbon-hydrogen bond, because that's one of the bonds that are going to be broken, and we need to multiply the energy given off, which is 412, by the number of bonds that are present there for that. And we have 4 of these carbon-hydrogen bonds, so we need to take that 412 and multiply it by 4. Right? And those are the amount of bonds inside of CH4 that needs to be broken. The next thing that needs to be broken is the chlorine bond. So we need to take Cl, and we need to find out how much energy is required for that. And in this instance, is 242. 242. So this is the amount of energy in total that would be required to break the bonds, because these bonds are the bonds that need to be broken. So then we need to do the same thing for the bonds that are formed, which is the carbon-hydrogen, right? And the carbon-chlorine, right? These are the bonds that are being formed. Also, you have a chlorine-hydrogen bond, right? Those are the bonds that are being formed. Now, if we were to try and simplify it, of all of this, 1 carbon-hydrogen bond was broken, and it was replaced with a carbon-chlorine, right? So this one was broken, all the rest remain the same. We have all this remain the same, but only one changed. And this here, this one changed, and this one changed. So we can simply check how much energy is required to break this bond, and how much energy is required to form this bond and that bond. And by so doing, we subtract one from the other, and we'll be able to figure out the total amount of energy that is produced. The question is blurry. Okay. All right. Anybody else have the question looking blurry to them? Okay, well, I'm gonna pull up this now. Okay. I hope this is a little clearer. All right. So in essence, I'm saying to you that the bonds broken and the bonds formed, we could add up the total that is required for it to give us the bonds broken and the bonds formed. And the difference in both of them, we can calculate, and it will tell us whether the reaction is an endothermic or exothermic reaction. All right, so next question. Many organic compounds which contain a halogen have chloro, bromo, or iodo in their name. The following diagram shows the structure of one chloropropane. And they give you the structure, then they tell you, draw the structure of an isomer of this compound. All right, so in essence, what they're asking you to do is just simply take this compound and find a way to move this chlorine from where it is here to another carbon. So if we were to do that, we'll have C, C, C. And we could have chlorine bonded here and hydrogens bonded all the way around. Right? In so doing, what we would have done is created an isomer of one chloropropane. So instead of it being one chloro, chlorine being on the first carbon, chlorine is now on the second carbon. So we'll end up with 2 chloropropane. Right? We end up with 2 chloropropane. All right, so some things that we are trying to achieve by the end of this lecture. This is taken from your syllabus. It's objective 14.5 in your syllabus. First objective, describe the manufacture of alkenes and of hydrogen by cracking. Distinguish between saturated and unsaturated hydrocarbons from molecular structures and by reaction with aqueous bromine. And then describe the formation of polyethylene as an example of addition polymerization of monomer units. We also want to be able to describe the properties of alkenes in terms of addition reaction with bromine, hydrogen, and steam. All right, so I have a short video that I want you to listen to before we move forward.
You should be able to describe what's meant by a functional group and by a homologous series. You should then be able to describe the combustion of alkenes, and finally, you should be able to describe the reaction of alkenes with hydrogen. And this is for triple chemistry students only. In the last video, we continued looking at alkenes. I'm showing you here the displayed formula of the alkenes ethene and propene. As we've seen, alkene molecules contain a double bond between the carbon atoms, and we can see that here. Now, because of the double bond, alkenes all react in a similar way. Scientists call the double bond the alkene functional group, and the words functional group mean the part of a molecule that determines how it reacts. Now, all of the alkenes have the same functional group, in other words, a carbon-to-carbon double bond. Scientists call molecules such as alkenes a homologous series. Members of a homologous series all have the same functional group. Each molecule in the homologous series has an extra carbon atom and 2 extra hydrogen atoms, and we can see that with ethene and propene. Over the next few videos, we're going to be looking at the reactions of alkenes. You need to make certain that you learn the reactions and the conditions. You're highly likely to see a question on this in your exam. We're going to start by looking at the combustion of alkenes. And remember that combustion means burning. Now, we looked at the combustion of alkanes in a previous video. As we saw, when we combust alkanes, we produce carbon dioxide and water. This is also true when we combust alkenes. However, combusting an alkene also produces unburnt carbon particles. That's because of a process called incomplete combustion, and you could be asked that in your exam. This means that alkenes burn in air with a smoky flame. We're going to look at incomplete combustion in more detail in a later video. Okay, the second key reaction of alkenes is with hydrogen. Scientists call this hydrogenation. I'm showing you here ethene reacting with hydrogen, and I'm showing the hydrogen molecule in green. This reaction requires a temperature of around 150 degrees Celsius. We also need to use a nickel catalyst to speed up the reaction. In this reaction, the two hydrogen atoms add across the double bond. The carbon-to-carbon double bond is converted into a carbon-to-carbon single bond. And as you can see, we've converted ethene into the alkane ethane. So reacting an alkene with hydrogen produces an alkane. You should be able to describe what's meant by a functional group and by a homologous series. You should then be able to describe the combustion of alkenes, and finally, you should be able to describe the reaction of alkenes with hydrogen. And this is for triple chemistry students only. You should be able to describe the reactions of alkenes with water and with halogens. This is for triple chemistry students only. In the last video, we saw that the alkenes are a homologous series. And remember that all of the molecules in a homologous series have the same functional group. So in the case of the alkenes, the functional group is the double bond. This means that all of the alkenes react in the same way. We looked at the combustion of alkenes and how the alkenes react with hydrogen. In this video, we're looking at how they react with water and with halogens. Again, it's really important that you learn these reactions, including the conditions. You can expect questions on these in your exams. So we're going to start with the reaction of alkenes with water. Scientists call this reaction hydration. I'm showing you the reaction of ethene with water here. As you can see, when we hydrate ethene, we make ethanol, which is an alcohol. The first key fact about hydration is that the water must be in the form of steam. The temperature must be around 300 degrees Celsius and the pressure around 70 atmospheres. And we use phosphoric acid as a catalyst to speed up the reaction. Now you'll notice that this reaction is reversible. So to increase the yield of ethanol, any unreacted ethene and steam are passed back through the catalyst. I should point out that this reaction might appear in an exam question on reversible reactions. Okay, we're going to look now at the reaction of alkenes with the halogens chlorine, bromine and iodine. Now, there are no special conditions for the reaction between alkenes and halogens. Alkenes react quite rapidly with halogens. I'm showing you here the reaction between ethene and chlorine gas, Cl2. In this reaction, we're making the product dichloroethane. As you can see, the two chlorine atoms in the chlorine molecule have added across the double bond. And once again, the double carbon-to-carbon bond has turned into a single carbon-to-carbon bond. This shows the alkene propene reacting with chlorine, and again you can see the chlorine atoms adding across the double bond. Now the halogens bromine and iodine react in the same way. I'm showing you here ethene reacting with bromine to make dibromoethane, and ethene reacting with iodine to make diiodoethane. You should be able to describe.
All right. So the next thing, I have another video here that I want you to listen to, and you let me know if you're hearing it.
Alkenes are also hydrocarbons. They consist of carbon-to-carbon and carbon-to-hydrogen bonds. However, they also consist of carbon-to-carbon bonds, okay? And that's basically the only difference between an alkane and an alkene. Now, what makes an alkane different from an alkene? I say again, it's the carbon double bond. And an alkene is a hydrocarbon that contains at least one of these double bonds, okay? And this group, this double bond here, makes the alkene unsaturated. In other words, it can undergo further reactions as a result of the double bonds, okay? Now, the double bond in the functional group is the functional group of the alkene, and therefore it is where reactions mostly takes place for alkenes. And the double bond allows for very, very many types of reactions to take place, which we're going to look at later. So this, as a result, makes the alkenes more prone to reactions and therefore generally more reactive than alkanes. Okay. So the main difference between an alkane and an alkene is the fact that there is a double bond. And the fact that there is a double bond occupies the possible number of bonds in which the carbon can be bonded to. Okay, so as a result, the general formula will be different. The general formula for an alkene is CnH2n for a molecule that has one double bond, which is the most common type of molecule. So, generally, for an alkene, there are twice as many hydrogen atoms as there are carbon atoms. Okay? Now let's look at the other possible alkenes that we have in the homologous series. And just like alkanes, alkenes can also exist as branched alkenes or branched molecules, such as so, whereby you have a main carbon chain, and attached to this main carbon chain is a branched carbon chain, or probably just a simple branch group in this case. So in this case, we have a branched alkene made up of a main carbon chain of 4 atoms of carbon, including a double bond there. And in the branch, we have 1 carbon atom. So the branched gives a prefix of methyl, and the suffix of the molecule, or the following part, follows the name of the main carbon chain. So in this case, we have 4 carbon atoms in the carbon chain, so it's going to be butene. So the whole molecule's name is methyl butene. Now, let's look at the reactions of alkenes. So as I said before, alkenes, as a result of its carbon double bond, it can undergo quite versatile reactions. And the 4 types of reactions that it can undergo are addition, hydration, combustion, and polymerization. So let's look at each and every single one of them. The first type of reaction that it can undergo is the addition of hydrogen to the carbon double bonds, or hydrogenation. Okay, so what happens in this case is that the carbon double bond is going to break, and the hydrogen bonds are also going to break, and each hydrogen atom would join with each carbon atom as a result, and this forms one molecule, and this molecule is an alkane. So an alkene, when it breaks the carbon double bonds and joins with 2 other hydrogen atoms, will form an alkane. And this is an example of hydrogenation. Okay, there you go. Sorry. Now, as I said before, alkenes are known as unsaturated, as in like they are prepared to be reacted. And when they have reacted with hydrogen, they will form an alkane, and an alkane is very unreactive. It is not prone to reactions. And as a result, they will become saturated. So this process can also be known as saturation, whereby an unsaturated alkene reacts with hydrogen to form a saturated alkane. Alright, so let's look at the next type of reaction in addition, and that is the addition of halogens. Okay, so in this case, similarly to the addition of hydrogen or hydrogenation, the carbon double bond in our alkene will break, and the bond of the halogen will break. So in this case, the bond of the bromine molecule will break, and each bromine molecule will join each carbon atom. So as a result, similar to the resulting alkane previously, you have a halogenoalkane. Okay, so when bromine reacts with an alkene, you will get a halogenoalkane. in that previous case, the name of that molecule was 1,2-dibromoethane, whereby dibromo means there are two molecules of bromine, two atoms of bromine in a molecule, and ethane just represents the main carbon chain of two carbon atoms. Okay, and this is a very, very important reaction, as because our reactants here are an alkene and a halogen. And in this case, we're going to be using an halogen of bromine in its liquid form, liquid bromine. Okay, and when an alkene is added to liquid bromine, it reacts and becomes a halogen alkane, as we talked about here. And what happens is, when you add a colorless substance to a brown liquid bromine, this will cause the brown liquid bromine to become colorless. So we've basically decolorized the bromine. And this is a very, very important visual test for the presence of alkenes. So how do we test for alkenes? All we gotta do is pour it into a solution of bromine water, and then it will decolorize. Okay, now let's look at the next type of reaction, and that is hydration. So similarly, in the previous cases, we are going to react with the carbon double bonds. In this case, our reactant is water and ethene. Okay, so when water in the form of steam reacts with an alkene, you will result in an alcohol. Alcohols are another homologous series we're going to talk about in probably the next video, whereby the carbon double bond will break and one of the hydrogen to oxygen bonds will break, and the OH from the water will bond with one carbon atom, whilst the H of the water, the remaining H of the water, will react with the carbon of the other alkene carbon atom. Okay, and this forms an alcohol. This reaction takes place at 300 degrees Celsius at a pressure of 60 bar, and phosphoric acid is used as a catalyst. Okay, so basically you have to remember these conditions, and this is the reaction to form an alcohol from an alkene. Cool. And the next and final reaction that an alkene can take place in is polymerization. Okay, polymerization is a case whereby the carbon double bonds of an alkene will break, and the alkenes can join other alkene molecules to form long molecules called polymers. So it's basically a single substance under certain conditions can react to form a longer molecule, and this is known as polymerization. So what you have is an alkene, it breaks its double bonds, and it joins with other alkenes which have also broken double bonds to form very, very long molecules. And each molecule can have up to 20,000 of these repeating units. Okay, so these two important terms that you must know. The first is monomer. The monomer is like the building block. It's like the bricks that form this polymer. And the monomer is the alkene, whose carbon double bonds will break. And the repeating unit is the representation of one unit of that whole polymer that is going to be repeated. So for example, in a polymer of 20,000 molecules, you're going to have 20,000 of these repeating units within the molecule, just joined end to end. Okay? So that's all there is. Oh, and you must learn about, and you must memorize the reaction conditions for polymerization. So, typically, polymerization, or generally, it will take place at a high temperature and pressure. At 200 degrees Celsius and 2000 bar for polyethylene. So that's just one of the conditions. But you just gotta expose your alkene to very high temperature and very, very high pressure for the ethene monomers to break its carbon double bonds and join together to form repeating units as a representation of a very, very long polymer.